So, good afternoon, everyone. Enjoy your lunch. It's certainly a very good spot to take your lunch here over lunchtime. My name is Olivier Frey. I'm here with Nils Goedeck, and we would like to present you on what these Akura plates enable us to do at InSphero in means of three-dimensional 3D cultures, and how these 3D cultures are made available to pharmaceutical, biotech, or academia. So InSphero is a biotech company located in Schlieren, Zurich, Switzerland, and it's all about spherites. So that's our main expertise that we have, and what you can see here is a flavor of different 3D spherites that we have engineered in the past couple of years. Liver, islets, tumor spherites that are able to replicate physiological functions of the different organ models. So for those who are new, spherites are assembled scaffold-free by an aggregation process. They are formed on non-adherent surfaces, in general 1 spherite per well. They can be assembled from different cell lines, primary, isolated cell, iPS cells. You can also create co-cultures of different complexity, mono, co, triple cultures when you need to replicate certain physiological conditions. And they require quite a small number of cells, in general something between 1,000 and 5,000 cells. So the liver microtissue spherite, as we call it, is one of the models that we have. We have cells that we take kind of from donors, they come cryopreserved, and then we aggregate them into this about 200 to 300 micrometer diameter spherite cultures, as you can see here in these cross sections. They come with a very uniform size, a very similar composition and function. And this is also what you can see, is that they preserve function, viability over at least 3 to 4 weeks, like 28 days. We have the ATP content that remains constant. Albumin, for example, is a secreted molecule very specific for the liver that remains functional over a longer period of day, as well as the metabolic activity. So such kind of characteristics have been made possible by a very stringent selection of the cells, internal QC, a patented 3D select process that we have enabled at InSphero. We have production checklists. We do regular characterization to ensure that these productions are always the same over a complete year. The second factor that made such kind of 3D cultures possible are these Akura Microplates that we have engineered over the past years. So what you can see on the right side is the Akura 96 spherite microplate, and it's a very specific plate made for these three-dimensional structures. So if you can see the cross section as we have it over here. No. So, as you can see it here on the right side, what you can see is actually the cross section, and it has a very special kind of funnel-like structure. And the funnel-like structure enables you, when you do a medium exchange, to have this tipping point there at this corner, and you can easily remove all the medium without removing the spherite that is located at this bottom, at this protected site, so that the spherite is not lost during a medium exchange. And this can be very important if you do multiple medium exchange in your journey of cell culturing, medium exchanges and staining, for example, over a 3 or 4 week experiment. The second point is we have a flat bottom and a very small opening at the bottom that allows you to quickly locate the spherite and do proper imaging through the flat oriented bottom. The second plate that we have is the high throughput structure, which is the 384 spherite microplate, that has a very similar structure on the inside, but is a little bit shifted and have an asymmetric design because we needed the space actually to bring down the pipette. So you can see here also the well shape on the inside, and again we have that short exchange ledge, as we call it, where the pipette can move down from the top into the well, where again you have the contact point and you can easily remove all the medium, but protecting the spherite that is located at the bottom of of the well plate. Again, we have a flat bottom. It comes in two versions, a larger, thicker bottom and a very thin bottom that is located and allows you to do high resolution imaging of the three-dimensional structure in this small little cavity at the bottom. I will go more detail of such an application in one of the talks that we have tomorrow in the session, so please come there. The plate also, due to the cell repellent surface, allows to aggregate the spheroid directly inside the microplates, and obviously, since it's an aggregation process, we can pipette the cell suspension into the well plate in all the plates at all the wells at the same time in order to get very uniform and the quick aggregation of those spheroids. So as I already mentioned, it enables us to do this production very uniform and reproducibly. So what you can see here is a standard scan as it comes in our certificate of qualification. On the left side, the 96 well plate, on the right side, the 384 well plate. What you can see, one spheroid in every well, same size, same morphology, aggregates very quickly, depending on the cell type, between 1 or 2 days, but up to 4 to 5 days if we have a more complicated structure as, for example, the liver microtissue. What you can also see that we have a minimal variation from well to well inside the plate, but you can also see at the bottom from another productions that the morphology and the size is very reproducible also from production to production. This is also shown in measurements that we have done. So here you see, for example, the diameter that we have measured over the complete plate at day one of the aggregation of different productions. Also, the viability is very reproducible from production to production. That ensures that if customers or our clients are getting the plate, they have the same characteristic today and in 1 year. The same works actually for the function of the plates. Also here, what we see is that the diameter remains constant over the 3 weeks of function of the liver microtissues, not only of one plate, but also for the different plates. And what you can see also at the bottom is that the CV of the diameter and of the ATP, or for the diameter size, below 5%, and for the ATP, we have a CV, a variation actually between the different productions in the range of 5 to 10%. So these data, and if you want to have more interaction, please meet my colleague Frauke that has a poster actually this afternoon from 2 to 3 if you want to discuss more in details about the production and the reproducibility of the spheroids that we have, for example, for the liver case. So the liver spheroid is a model that we use, for example, for drug-induced liver toxicity, so to evaluate on how compounds are affecting the liver in means of safety aspects. So what we routinely do is that we test 2 different compounds using a dose response curve, 7 different concentrations in a journey of 1 or 2 weeks, basically expose it, and then we measure the IC50 of these reference compounds in every production. So what you can see here is that the dose response curves, they are nearly identical from a production A to production B. And we recorded actually these IC50s over several experimental runs over a year. And what you can see on the one hand is that the CVs are very reproducible, but the Z prime factor that we have for this specific assay is on the one hand above 0.5%, and on the other hand very reproducible over time. Our CEO Jan Lichtenberg will give a talk on how we have implemented actually this DILI assay using over 150 different FDA approved drugs to replicate actually the in vitro predictivity of the assays and compared it with the in vivo case. So these are the spheroids that we are producing in a weekly routine, and we test the compounds here internally, but we are also testing, or we also make these microtissues available to pharma, academia and biotech worldwide. So we ship them after the production, fresh, assay ready to the different companies. And in order to do this, we have constructed a patented unique shipping solution, because due to the fact that the spheroids are suspension spheroids, we need to keep the plates upright during the complete shipping process. And that's why we have engineered a special container, which is a large spheroid, where actually the plates are loaded inside, and the large sphere is actually swimming inside a square box, as you can see it on the left side, so that it remains always upright to get safe and functional to the customer sites, where we can unpack this sphere and then directly use the spheroid upon reception. So that's the fresh and live shipment of the microtissues as we provide it to customer. But we recently also launched a new way to do it in a cryopreserved way, and that's why I'm going to switch to my colleague Nils that will present you our Arctis portfolio.
Thank you, Olivier, and good to see you all. So welcome to our presentation, and it's a pleasure for me to speak again about the Arctis products. Arctis is short for Always Ready Cryo Tissues. Last year in Boston, I went all in with the details. I'm not doing a test, so who has seen it last year, but nonetheless, I will give a few repetitions, I would say. So first off, the question is, why on earth did we develop that? And the good reason is because since we are doing this on a day-to-day basis, on a week-to-week routine, the cost is reduced by sheer optimization of the process. Secondly, we have the control over the whole process so narrowed down that plate by plate, exactly what Olivier was presenting before, is what we can also rely within the frozen products. And we have developed, we presented about 20 cell models last year, and that's exactly what it is. It's a whole range, a whole portfolios of tools. However, in contrast to the one that has been presented before, we ship it to you in frozen. So none of the big containers, because what we are talking here now are oncology models. And oncology models, it may be easy if I ship it we are based in Zurich, ship it within Switzerland, I can always guarantee it's there in 6 hours. However, if I have to ship it across the pond, it may be 24, it may be 72, it may be 96, I don't know. And so for an oncology model, if you want to start always the same time, that's almost impossible. And even if you narrow down all the customs and everything. So the idea is, you have the 96 well plate frozen. There is a cell solution that has been optimized in number of cells, cryopreserved, etc., etc. We have a rather detailed thawing process. So all you have to do is take it out of the -80, warm it up in the incubator, feed it fresh medium, we call it the aggregation medium. You dilute the cryoprotectant, centrifuge them down, give them fresh food. And I always keep on saying, do this Friday morning, let them have a weekend, you have a weekend, and you come back on Monday and you see the first little set of spheroids. They are already, some are quicker. I will show 3 different examples here. Some are already done on Monday, some take to Tuesday or Wednesday, but the early next week you can start dosing and start testing your experiment, which is super convenient, and you don't have to think, oh, I need to order 2-3 packs. No, I keep on saying, order once a pack, all you need for the next 6 months, and you're good to go. So the testing itself is always, that's what we do. So, and also what we suggest. So thawing first, and then you let them aggregate. So you see, I think the contrast is just about enough. You have them all sitting in one corner. And then with HCT116 is a colorectal cancer model. It's very common, it's well researched, and also super robust. So you have already this little spheroid, and that is then growing. So on the top right, you see how much it grows. It's a bit bigger than 200, 280-ish, and then goes all the way up to 500, 600. Remember the diameter of our opening, the round grayish part in the images is about 1 millimeter, so you start with under 300, so this is what it is optimized to give you the whole 11 days or 12 days of growth without overgrowing the well. Having a whole selection of cells, we checked, okay, how good do they do? The red line is perhaps difficult to see, so we made a whole bunch and tested the red ones with staurosporine. Staurosporine we picked because we had to pick one compound that works for all, so that's the one we are working with. And then part of the plates that we have frozen over the weekend, we basically say 2 days, we test them, 3 months later from the same batch, 6 months later, so this is what you see here. And it basically makes no significant difference whether they are fresh or frozen, so that's the message what I want to show here. And so that was what we presented last year. It's like it works half a year, it's all great. Now application-wise, so we have started developing a network of applications where other companies, like here, can test their tech. Since I cannot show their application, I'll show what we did. And so I went with our oncology team and said, like, what else apart from staurosporine is kind of standard? Anything else? So we went with, we have 3 models that we put in a starter pack, we call that. This is the A549, it's a highly researched cell line. And you can see that those cells, the more erlotinib, this is an EGFR blocker, the more you give, you get a significant decrease in growth. And you can also see that the IC50 for them is in the same range. It's not identical, but it's very close together. Same for paclitaxel. Your cells, whether they are fresh on the left or they are cryopreserved, the model still holds very well. Another part of our starter pack is the T47 breast cancer, also highly researched. We perhaps could have focused more towards the right-hand side, so you see the data. So that was a quick test that we wanted to show just to demonstrate the whole principle holds still. It's, I think it's, for engineering here, it's exactly what it is. Does it robustly. And you see, if you look into the wells, the concentration is always one column. They just look one like the other. So that's very satisfying and I think also convincing. And even an HCT116 is just such a textbook cell line, so you can pretty much do whatever you want with that. And that's what I'm saying. If you have a imaging process where you want to show this, that your instrument can do this, where your software can do that. Right now, this is all only bright field. There could be a fluorescent marker in it, or any other kind of add-on that you want to demonstrate. And with the cell solution, you can incorporate it right from the start. And I've been asked in the beginning, I was like, wouldn't it be better to freeze down whole spheroids? Wouldn't that be quicker? Well, it would take a whole spheroid also 2, 3, 4 days to recover from the freezing stress. So do you save time? Probably minutes. So no, not really. So not enough at least to make the big effort. And so, and also the beauty is that you can incorporate external nanoparticles, for example, for labeling. So I think that's it's a really good system. It says Monday. I'm being in my poster tomorrow. Sorry, that's a hiccup. But we already uploaded the slides. And if this is something you consider for trying out, so we call it the starter pack. It has 2 plates of each of the 3 cell lines I was just demonstrating here. It's all together as a one-stop solution, and it gives a good start and indication. And then once this is set up and you say, like, yeah, but we still need the other ones from the cell lines you presented last year. Sure, then we make that as well. But this is where I always say, go start and have the first successful images with your own tech and basically join the InSphero family in terms of data. So with that, so we are just over there. at 26-23. We have the posters that Olivier already also mentioned and another talk. So thank you very much for your attention, and I wish you all a great experience at SLAS 25. Thank you. Questions?